So let's take a look at intermolecular and intramolecular forces. Let's assume that this is a kind of closed container, and these white circles you're seeing are gases. Okay, these are let what should I call them? Like, let's call them hydrogen gases. Okay, each of them are hydrogen gases. They're moving around randomly within this container. Okay, now there is a force of attraction between each gas. So this hydrogen gas will be attracted to this hydrogen gas, and this hydrogen gas will be attracted to this hydrogen gas, and so on and so forth. So there will be a kind of attraction between each gas molecule. You understand? And that force of attraction, this force of attraction between the gas molecules is called intermolecular force. So intermolecular force basically is the force of attraction between two molecules. So the force of attraction between an hydrogen gas molecule, that's H2. Okay, let's say each of these white thing you are seeing hydrogen gases are H2. So the force of attraction between this H2 and this H2 and this H2 and each H2 here is called intermolecular force. Now for intramolecular force, this one is let's take for example H2 molecule. I'll use the same example again. I have H2 molecule, something like this. So the kind of bond or the kind of force holding atoms within a molecule together is called intramolecular, which means that this bond here, or this force here, is intramolecular bond or intramolecular force. So the difference between intra and inter, we can say that intra is within while inter is between. So the force between two molecules is intermolecular, and the force within a molecule, that's between the atoms in that molecule, is intramolecular. Okay, so in this video we're talking more about intermolecular forces. Now basically there are two main types of intermolecular force. One, we have the London dispersion force, otherwise called van der Waals, and we have another kind of intermolecular force called dipole interaction. Okay, let's start with the first one. When I say LDF, I mean London dispersion force, so I'll call it LDF for short. Now LDF is a kind of intermolecular force that is found specially in non-polar molecules. I said specially, which means that you can also find them in polar, but they are peculiar to non-polar molecules. So non-polar molecules contain a kind of force called London dispersion force. And one thing to notice is that LDF is a weak force. It's not as strong as dipole. That means between these two, between LDF and dipole is much stronger than LDF. How can we actually explain LDF? How can we actually explain it? Let's put it this way. Take for example, I have this is a molecule. This is H2 molecule. This is other H2 molecule. So let's explain what LDF actually is. Now around the molecule, around an atom, there is usually electrons, right? There are electrons around this molecule. They're moving like randomly. They're moving around the molecule. They're not in one place. They're moving around. So let's just do something like this to represent. Let me use this to represent the electron cloud. So this is the electron cloud around this here is electron cloud, okay, around this molecule, same as this too. So this is electron cloud around this molecule. Okay, now electrons are constantly moving around the molecule, moving around an atom in a molecule. Do you understand? So like we cannot really tell the position at which the electrons will be. So at a particular time, they might be clustered in a particular region. At a particular time, they can be found, they may be clustered, there may be more electrons in this region than in this region. Let's first quote an assumption. Let's assume that at a particular time, there were more electrons on this side. The electrons are moving randomly, right? So at a particular time, let's assume that there are more electrons on this side than they are on this. I think you get my diagram. Than they are on this side. So there are more electron clouds here than this side. Okay, now since we have more electrons on this side, it will give this side a partially what negative charge, and thereby giving each other side what a partially positive charge. You can see now this has created a kind of temporal, we call it a temporal dipole. It's not permanent. Okay, that's called the kind of temporal dipole in H2 or in the molecule. Now, if this molecule now comes close to another molecule that was formerly, like come close to this molecule now that was formerly looking something like this. Now, don't forget that positive and negative charge, what they do, they attract, right? So this partially positive charge will attract the electrons here, make them to be clustered on one side. Let me draw just to show you what I'm trying to talk about. Let me give you a diagram. But in this case now, because of this partially positive charge on this hydrogen molecule here, it induced a polarity in the other molecule, making the electrons to move to this side since positive and negative charges attract. So making this side now partially what now? Partially negative, making this part now partially what? Positive. Now what have this molecule done? Sorry. What have this molecule done? It has simply induced a polarity. This molecule here, this hydrogen molecule now, has induced a polarity in this other molecule. So this is basically what we call LDF. So the kind of attraction now between these two temporal dipoles now, okay, is these two between these two temporal dipoles now is called London dispersion force. So we can also call it induced force or induced dipole force. Induced dipole force. So as you can see just from my example, you can see that this molecule over here induced a dipole in the other molecule. Now that's what they call London dispersion force, LDF, and as I said, it forms a temporal dipole which induces a dipole in the other molecule. So the kind of force between two hydrogen molecules is a particular kind of intermolecular force called LDF, London dispersion force, or Van der Waals force or Van der Waals. And one thing that must be noted is an increase in the molar mass of a molecule will cause an increase in the London dispersion force. What do I mean? Take for example, I have H2 as I use an example now, H2, and I have CH4. Now they are both what? They are both non-polar. This means that the kind of force that will exist between the molecules is what? Is London dispersion force. But which we have a greater London dispersion force, H2 or CH4? Looking at the molar mass of H2, molar mass of H2 should be something around 2 grams per mole, and the molar mass of CH4 is something around 16 grams per mole. Now, because of the molar mass of CH4 is higher than the molar mass of H2, CH4 will have a stronger LDF compared to H2. It makes sense because this is bigger than this. Like the molecular size is bigger than this. As the molecular size is bigger, it means that we're going to have more electrons. We're going to have more electrons. And if we have more electrons, it means that the London dispersion force will also increase since we have more electrons. So an increase in the molar mass of a particular molecule will cause an increase in the strength of the LDF. So if I have C5H10, this is also non-polar. So which now we have the greatest LDF? Yes, you're correct. So C5H10 will have the highest LDF because it has the highest molecular mass. Now for dipole-dipole interaction, this one is only found in polar molecules. This means that you can't find dipole-dipole interaction in non-polar molecules because from the start, non-polar molecules as well imply they are not polar. That means they cannot produce dipole. Then they can't produce dipole. So hence they can't have dipole-dipole interaction. So dipole-dipole interaction is peculiar to polar molecules. Take for example, I have HCl. HCl should look something like this. Let's say I have multiple of, I have like 3 or 4 HCl molecules in a beaker or something. Okay, because of the difference in the negativity of chlorine and hydrogen, there will be a shift of electrons towards chlorine, giving chlorine a partially negative charge and hydrogen a partially positive charge. But that goes for this as well and this as well. Now there'll be an attraction between this HCl molecule and this HCl molecule. The dipoles, I told you what dipoles is, this polar dipoles or this bond dipoles. The dipoles now will interact with each other. There'll be a kind of attraction between this negative dipole and this positive dipole. Do you understand? Also be for the attraction because negative and positive charges attract. Also be for the attraction between this and this as well because this is what partially negative, partially positive, partially what negative. So be an attraction between the two of them. So what is interacting? This is my example. You can see that dipoles are interacting. This dipole interacting with this over here. So that is called dipole interaction. So the kind of force, intermolecular force between HCl molecules is dipole interaction. Take for example again, I have water molecule. Let's assume I have a lot of this. I have other water molecules as well. So we know that water molecule is polar because this will be partially negative, this will be partially positive. So the electrons here will be pulled towards oxygen, same goes here. And this also, same thing happens in all the molecules. Looking at this now, there will be a kind of attraction between this water molecule and this water molecule. You can see we have a positive dipole and we have a negative dipole. So what will happen? There will be an attraction between the positive and the negative. So there will be an attraction here, something like this in red. There will be an attraction here as well. This will have a positive, we have a negative over here. So there will be a kind of attraction here. You understand that? So this force or this bond is called dipole interaction. This particular dipole interaction is a special type of dipole called hydrogen bond. So hydrogen bond is a dipole interaction. So there are like 4. Let me clear up the screen so that the space. There are like 4 types. 1, we have hydrogen bond. 2, we have dipole induced dipole. We have ion dipole, and we have ion induced dipole. So you don't need to worry about the rest of them. One that you should just have in mind for now. Maybe we'll make more videos on talking about the others. Okay, let's talk about hydrogen bond. Hydrogen bond is a special type of what of dipole interaction. Hydrogen bond is the bond between, I like calling it H phone. By H phone I mean F represent fluorine, O represent oxygen, N represent nitrogen. So the bond between hydrogen and fluorine, the bond between hydrogen and oxygen, the bond between hydrogen and nitrogen is what we call hydrogen bond. So let's come back to our water molecule. Water molecule now, what do we have? The interaction was between these two dipoles, right? That's between oxygen, this oxygen atom here, and this was hydrogen. It falls in the category of H4, isn't it? So we say that the bond between water is not just dipole, but what? But hydrogen bond. And let's take a look at ammonia. As you know again, we know that hydrogen and nitrogen have different negativity, which means that the electrons there will pull towards nitrogen. Here also pull towards nitrogen, also pull towards nitrogen in this direction, which you are going to have a net dipole in this direction. Okay, and that will give nitrogen a partially negative charge and give the hydrogens here partially positive charge. Let's apply this to the other molecules. Let's examine what kind of bond do you think will be between this ammonia molecule and this ammonia molecule. You can see we have a positive dipole and a negative dipole. That's on the hydrogen and the nitrogen. There will be an attraction between this nitrogen and this hydrogen. Okay, there will also be an attraction between this hydrogen up here and this nitrogen. So the attraction here is an intermolecular force. A particular kind of intermolecular force. Since we have dipole-dipole interacting, they say this kind of intermolecular force is called what? Dipole-dipole interaction. Now, can I ask you a question that which kind of dipole-dipole interaction do we have here? In this case, because of we have the interaction between this dipole and this dipole, right? And this is what? Hydrogen. This is what? Nitrogen. And don't forget, hydrogen bond is a type of what? Of dipole-dipole between HFON, that's between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and what? Nitrogen. In this case, now we have bond between hydrogen and what? And nitrogen. So hence this kind of dipole-dipole is called hydrogen bond. Lastly, we have hydrofluoric acid. We know again that this is a polar molecule because fluorine is more or less negative than hydrogen. That will give fluorine a partial negative charge, hydrogen a partial positive charge. The same goes for this molecule as well. So you can see there'll be an attraction between this fluorine and this hydrogen because they have opposite charges. Do you understand that? Opposite and partial charges. So this is a dipole-dipole interaction, but a special type called hydrogen bond because it is between hydrogen and what? And fluorine. And one thing you should note as a takeaway is that hydrogen bond is the strongest dipole interaction you can have. The strongest dipole interaction is what? Is hydrogen bond. But it's not the only one we have. We have dipole, we have hydrogen bonds, we have dipole induced dipole, we have ion dipole, and we have ion induced dipole. Okay, but hydrogen bond is the strongest of them all. Just to recap, there are two types of intermolecular forces. We have London dispersion force and we have dipole-dipole interaction. LDF is found in all molecules but peculiar to non-polar molecules, which means that we can find LDF in polar molecules but they are peculiar to just non-polar. And non-polar molecules have LDF, and the greater the molecular mass of that compound, of that non-polar compound, the stronger the LDF. While for dipole-dipole is the interaction between a dipole and a dipole, as the word implies, and there are four types. We have hydrogen being the strongest, we have ion induced dipole, we have ion dipole, and we have dipole induced dipole.